Hi, my name is Guy Samborski. I'm a chemical engineer and consultant specializing in powder technology and crystallization. I will discuss today microgravity experiments in space, a possibility that most of you would probably consider far-fetched or even science fiction. However, it recently becomes more and more accessible for researchers in industry and academy. But why do we want to go to space anyway? What is the significance of microgravity for chemistry and biology? This is Jessica Meyer, an astronaut who spent recently 7 months on board the ISS and made history participating in the first all-women spacewalk. She is a healthy, energetic young lady. However, after 7 months in microgravity, almost every system in her body, as well as in other astronauts' body, experienced extreme changes. Reduction in bone mass, muscle atrophy, slower hair growth, and many more. These are equivalent to about 10 years of aging. Most of those changes are of course reversible. While they are imposing a challenge for future space travel, these changes are an opportunity to learn and improve the health of Earth residents. I will focus on the effect of gravity, or the lack of gravity, on chemical and biological reactions. Gravity is an actually important variable in every equation in physics and thermodynamics. However, we neglect it simply because we take it as a constant. These two examples show the main phenomena that completely disappear in microgravity. Sedimentation. Heavy particles will not sediment to the bottom of a vessel. Buoyancy. In this experiment from 2017, an oil in water suspension that normally would separate in few seconds remains stable for several weeks. Natural convection. See how a candle flame in space is round and blue. On Earth, hot gases go up, away from the flame, in a process called convection, and as they cool down, they change their color. Natural convection is the strongest mechanism for heat and mass transfer. Moreover, in the lack of microgravity, other phenomena that we tend to neglect on Earth become dominant: surface tension, Marangoni convection, laminar flow, and interface layers. These altered processes make all processes, including those in our body, behave differently. The field of my work is focused on crystallization. I imagine crystal growth on Earth as a ship tries to dock in a very stormy sea. Around the growing crystals, there is a sharp decrease in concentration, causing density changes and turbulence. As a result, molecules are not approaching the crystal in a uniform way. Therefore, there are voids and misalignments that impair the quality of the crystal. However, in microgravity, the boundary layer is still and linear, and the crystal grows in a more organized way. In addition to minimizing convection currents, microgravity reduces molecular diffusion rates and suspension remains still. There are no collision with the walls or other crystals. The result is a larger crystal with a higher order of crystallinity and higher purity. There is also a possibility to obtain unique polymorphs. One of the applications that nowadays applied commercially in the Japanese section of the ISS is crystallization of proteins for the development of biological drugs. The biopharma company need to characterize the three-dimensional structures of the proteins that are either the drug candidates or the targets. This is done by crystallography, and for that purpose, a perfect crystal is required. But proteins are very large molecules, and it is very difficult to crystallize them on Earth. Very nice crystals are obtained in microgravity. Several drugs were already developed with the assistance of space crystals. My research is focused on polymorphism and crystallization of small molecules. In this case, we crystallized an amino acid on a parabolic flight. The crystallization reactor was placed in an airplane performing 16 sharp dives, providing 30 seconds of microgravity in each dive. 30 seconds were enough to receive the more stable polymorph A. Although most growth was later on the ground, it was enough that the seeds will be created in microgravity, and this has an important implication for commercialization. If we want to obtain superior crystals, we need to make only the seeds in space, accounting usually for 0.1, 0.5 of the entire quantity. It means that this approach could be applied to commercial manufacturers of certain drugs. This experiment was performed using a sample received from Teva API. On board the ISS, we grew a drug substance notoriously known for its thin, needle-shaped particles, leading to stickiness and poor flowing. In microgravity, the aspect ratio was altered very easily, yielding 100 times thicker crystals. Furthermore, single, defect-free crystals were obtained. You can see how the X-ray diffraction pattern of the space crystals is sharp and symmetric. This enabled the researchers to determine the exact enantiomeric structure of the substance. How far are we from industrial applications? There have been already 3 revolutions in utilization of space: communication, Earth observation, and GPS. All started with government and military application, continued for high-end civilian applications, and now they are in everyone's pocket. Part of our daily life, even for not so important applications, such as shopping or sending pictures of cats to our friends. The revolution starts when there is enough accessibility that creates a critical mass of users, leading to a burst in idea and utilization. We believe that the next revolution in space utilization is for life science, chemistry, and biology. It started with scarce research dominated by the Americans and the Russians during the Skylab, the Mir, and the Space Shuttle's era. A huge boost was generated by the International Space Station, where 6 astronauts are stated performing many experiments. The next step is the availability of nanosatellites, providing low-cost, quick access to many reactions, including such that are too dangerous to carry on board the ISS. In about 2 years, a new generation of unmanned space shuttles will provide frequent flights. Using miniaturized, automated, remote-controlled labs will enable fast and complex research and even manufacturing of significant quantities in space. Thank you for your attention. If you have questions, please contact me.